So hello again. Tonight we're going to talk about repurposing retired satellites for radio astronomy. The radio astronomy community could use some radio specific space telescopes to do some observing that they're not observing currently. There's certain wavelengths that don't pass through the atmosphere, and we need some way of getting some radio astronomy satellites up there, but it takes decades, it costs billions of dollars, and who's got time or money for that? So let's just reuse what we got. So we're used to seeing these giant parabolic dish antennas on the Earth, ground-based communications, talking two-way communication to orbiting satellites. So like the Hubble Space Telescope, the GOES weather satellites, your favorite satellite TV service, entertainment, military relay satellites, spy satellites, clandestine satellites, or talking to deep space probes like the James Webb Space Telescope, Gaia, the new Euclid, the Parker Solar Probe, or Juno around Jupiter. Another purpose for these giant parabolic dishes is radio astronomy, or as they call them, big ears, because they typically are only listening. They'll be listening for radio signals from galaxies, known as quasars or quasi-stellar radio sources, or pulsars, which are a form of neutron star. But these are what we have on the ground for listening. So why are these things so big? Well, if you've studied radio propagation to any degree, you'll notice that the electromagnetic spectrum, as you get down to lower frequencies, well below light, well below infrared, down into radio, that the actual wavelength becomes very much longer. Are the antennas this big because the wavelength is so much longer? Not really. It's the signal strength is so low, they need a very large diameter dish to collect up all of the weak signals and amplify them. If you want an example, 10 megahertz frequency is about 30 meters long or about 98 feet long, and these large dish antennas are several times that diameter. So even the gigahertz frequencies, which are very small portions of a meter, almost a millimeter or submillimeter, they still use large dish antennas. But there's only certain frequencies that they can listen in on or communicate with, because the moisture in the Earth's atmosphere blocks certain frequencies. You can see, I took this image. Well, I didn't take it. I grabbed this image, but then I added in blocked and passes and attenuated. And the ones that are blocked, you can see the 100% obstruction. I was like, you can want to listen at that frequency all you want, but you're not going to hear any of it because it's blocked by the Earth's atmosphere. The one that has the dip down where it says passes, the material, the gases and the moisture of the Earth's atmosphere do not block these particular wavelengths. So you can freely hear things in space at those wavelengths, and you can use those wavelengths to talk to satellites or talk to space probes or talk to astronauts on board spacecraft. And so that's the reason why they use specific frequencies, is because those frequencies will pass through the atmosphere. But sometimes they'll use other frequencies. You can see the attenuated ones where they have the wiggly lines with dips. If you have a big enough dish, you can listen to a weak enough signal and amplify it enough to actually get that signal to go through the Earth's atmosphere. But you got to be picky as to what frequencies you're going to listen. You can see the rainbow there. That's light, because light goes through the atmosphere. That's why they do things a certain way. Okay, now I know nobody can read this picture. It's just to show you how much detail there is in it. The United States has an organization known as the Federal Communications Commission. They are responsible for logging, registering, giving approval to licensing for transmitting on certain wavelengths. And you can see the frequencies that are lower, the longer wavelengths, are towards the top of the chart. And the chart actually zigzags like a giant Z, stretches out. So you have the lower wavelengths, top left, and as you get down towards the bottom right, you're up in the, nearly terahertz. You're well up into the gigahertz range, and you can see all the little different color boxes. And if you look on the left side of the chart, you can see different boxes have different little text next to them. And that's the purpose of the allocation of that particular wavelength. So different wavelengths have different purposes. And a wavelength that's, let's say, not going to make it through the atmosphere, that might bounce off the atmosphere, it's locked into doing things that only work down here on the ground. Like, I don't know, mobile radio kinds of things, like your cell phone. You don't really need your cell phone to transmit out into space, but you need your cell phone to work a certain distance. So signal propagation distance, propagation through the atmosphere, power of what you're transmitting on, that determines where all these little boxes wind up. And there's a whole collection of boxes that are for radio astronomy. So I took a closer up picture of it. All the little boxes that are yellow, and don't be confused by the ones that are orange, because yellow is a little different color. If you look on, let's just go down the rows, 1, 2, 3, 4, 5. You go down to the 5th row, towards the right-hand side, you can actually see some bright orange, some middle orange, and a yellow one. The yellow one is for radio astronomy, and you can actually make out like short word radio, long word astronomy. So you can see that patchwork quilt of, well, there's not a whole lot dedicated to radio astronomy. Like, nobody else uses it for radio astronomy. Wherever you see multiple colors in a single row, that means y'all got to share. If there happens to be a particular frequency that radio astronomy is allowed on, it may be, like 20 gigahertz worth of bandwidth. But the FCC will also allocate, for propagation purposes and power purposes, maybe a particular kind of ground-based radio transmission that goes short distances. And it'll be transmitting on a certain frequency that's in the same band as radio astronomy. So the radio observatory, if there's any of those transmitters nearby, they'll have to carve out a notch and be cooperative and say, okay, that particular frequency for that particular bandwidth is not ours to listen in on. We have to put up with somebody else transmitting. But since we know exactly what it is, we can carve that out. So you have to share. Here it is, zoomed up a lot. Now this is just the slice from 110 to 160 gigahertz. So this is down in the millimeter, sub-millimeter range. And you see the tall group of colored boxes at the center. Fixed satellite space to Earth, mobile satellite space to Earth, radio navigation satellite, and then radio astronomy. So radio astronomers have to share with all these other things. Now think about it. If I've got a satellite that is in geostationary orbit, that's going to be a fixed satellite transmitting space to Earth all the time. So as a radio astronomer, I've got to find out, okay, am I within the footprint of that transmitting satellite? What are the frequencies that they transmit on? And I've got to carve those out of my radio astronomy observations. Mobile satellites, a little trickier. That's a satellite that passes overhead, and I need to go learn when it's going to pass over my observatory and to maybe not listen during that time. And then radio navigation, that may be like old style Orion. And so I have to know where that's transmitting from and what frequency it's on. And all of that, the radio astronomy community has to put up with, has to deal with, because y'all got to share. But you can see the patchwork quilt here, how many different little pockets there are for radio astronomy. And if it turns out that nobody is near you transmitting on the frequency you want to listen on, even though you have to share, you have no conflict. So at your location of your radio observatory, like Green Bank in West Virginia, inside of a circular mountain range, yeah, you got to share, but don't care because nobody needs to share it with you. But there are other places where there could be things actively transmitting all the time. And so you have to know what frequency they're transmitting on. So it's up to the radio astronomer to look up who they're sharing with, find out when they're going to be transmitting, find out whether it's fixed, as in always coming from that direction where the satellite's parked, or cruising overhead every so often. Yep, ignore it during this time period because that's just the satellite going overhead. So the radio astronomy community has to deal with that. That's just day-to-day business. The radio astronomy community can deal with the conflicts, but what about when the radio astronomy community is trying to listen where they don't have radio astronomy allocated? They're basically, I know I don't have to share at this particular band, but I want to listen because due to astrophysics, I found that there's a particular frequency that my radio telescope needs to listen to that we didn't originally think of as for radio astronomy, but I'm going to listen anyway. So the square kilometer array, this is a new array of radio telescopes that they want to put up a couple of places around the Earth, and it's going to be listening in several bands. They've got several different kinds of antennas. They've got parabolics and sticks and things like that. Well, the one that's just sticks, they want to listen in on a particular frequency that is in use by satellites, a lot of satellites on lots of frequencies, but the band itself is fairly wide and the FCC hasn't allocated all the different channels to satellites yet. There's more to come, but the radio astronomy community is saying, hey, FCC, not only do we want you to stop allocating for new satellites in that band, we want you to go claw back those frequencies from the satellites and have them go to another band, because we just found out in astrophysics something new that we discovered, that, hey, there's something happening on exoplanets that we might want to do radio spectroscopy on to detect certain elements in the atmospheres of exoplanets around stars. But we can't best listen if we have all these satellites transmitting in the same band. And, it's hard to carve them all out. So we just want you to tell them to, we want this band now and get those guys out of it. But think about it this way. If I launch a satellite and that satellite was granted official approval by the FCC to transmit on that frequency, it's the design of the satellite. You're not going to be bumping it up to a different band or down to a different band just because they design the electronics to say, transmit within this allocated band and make sure you don't have any spurious transmissions that would get off that band and conflict with somebody else. The square kilometer array is fighting an uphill battle here. If they get the FCC to stop allocating, they've still got the satellites that are going to be up there for maybe 5 to 25 years transmitting in their officially allocated frequencies, and you just got to deal with that. So it's a balance of things. The radio astronomy community has to deal with other things that aren't quite so easy to deal with. How about, they got to share with others. Talk it out amongst yourselves. Figure out what's going on. Yeah, it's a burden, but somebody's got to do it. How about somebody launching something into orbit that doesn't have the greatest transmitter? It doesn't have walls that will stop it from bleeding over into other frequencies. That's bad enough, but you have no control over that because some of these satellites are international and the quality of what they put up is the quality of what they put up. What's even worse is if you have a frequency that happens to be a harmonic of something that is very popular on the ground, and you make the transmitters cheaply, because you got to sell them cheaply because they happen to be in millions of automobiles, as in, let's say, I don't know, radar to detect whether your car is going to run into something. If you make the transmitter for the radar cheap enough, it's going to have spurious harmonics that bleed over into, oh, look, it's right next to a radio astronomy band. Bad enough, but the Green Bank telescope, there's a notch in the mountain range around them that happens to face towards a highway where a lot of newer model cars are driving towards the telescope, and they've got their radar on the car. And, oh, look, there's another cheap knockoff radar on that import vehicle that is bleeding over, affecting radio astronomy. Well, what are you going to do? You just have to wait until the car drives by. So you just, slice out that frame. Or in optical astronomy, hey, an airplane went through my stack of images. Well, just take out that item from the stack. So it's just what they have to do. And if you get somebody truly illegally transmitting in your radio astronomy band that should not be there, let's say you looked at that stack of things you have to share with, and somebody else came in there and is transmitting on a convenient frequency that happens to have a purpose other than what they're using it for, just give the FCC a call. They'll be glad to send out the truck, track them down, and issue them a notice, which is supposed to make them stop transmitting. And if they don't, and if you call them out again, they get a fine. If they keep doing it, they get a bigger fine. If they're ignoring the bigger fine, they get jail time. So, it's serious stuff to make sure that people aren't abusing the allocated radio frequencies. So I don't know how many people are aware of this, but there are multi-generational geostationary satellites. These are satellites that get put up into orbit, and then you expect to get continuous service from them. Let's say weather satellites. Everybody wants that daily picture of the cloud cover over their house. And every morning they've got a little pop-up that shows up and shows them the cloud cover. You just take it for granted it's always going to be up there. If you did that with just one satellite at a time, if you happen to have a malfunction on that satellite, how long will it be before you can get a rocket with a new satellite up into orbit to replace that one? Could be years, could be a decade, could be a good portion of a decade. So what do? Well, you put up a satellite, it offers the service, and then right behind it, like 2 years later, you put up another satellite that you park offset from that satellite. So you've still got the main satellite still doing its daily weather map kind of thing. And then you've got another satellite that's waiting in the wings, so to speak. It's literally in the wings of the other satellite. It's also geostationary. It's just a little offset. Well, if that satellite has a problem, you move it out of the way, you move that satellite into the position, and within like a portion of a day or better, its replacement is back on the air doing its daily satellite weather map. Nobody knows that. That's just something that it's always up there. It's always going to be up there. No, there's a plan. It's multi-generational geostationary satellite. And the GOES weather satellites actually have letters for the next up satellites. So you see GOES T becomes GOES West. And they've got a GOES East and a GOES West. GOES is just a name. It has nothing to do with going somewhere. So they put up a satellite towards the east, put up a satellite towards the west, and as the next up satellite comes in, it gets the next alphabetic letter. So Q, R, S, T, U, V. I don't know what happens when you get to Z. I guess they go to AA, like the old Sears and Roebuck catalog used to. But when it's time to replace the current GOES West, they'll take whatever the next GOES letter is, like GOES S or GOES T is going to become the next GOES West. And when the former GOES West goes out of commission, it gets back its original letter and it gets parked. And if they have enough fuel on board and there's no malfunction, it's just older technology or it's about to run out of fuel, they'll move it in the same orbit over the Pacific Ocean where there ain't nothing. There's no land masses. There's nothing profitable to be sending the picture down to. So they'll move it out over the Pacific and park it there. So that's called a graveyard orbit. And the new GOES T becomes GOES West and nobody the wiser. Well, they do this with weather satellites. They do this with military communications relay satellites. They're called TDRS. And they do this with secret surveillance satellites. The last known program I'm aware of is something called Orion or Advanced Orion. That's just what they call the program. The actual names of the individual satellites are numbers from the National Reconnaissance Office. And you can see sometimes SpaceX doing one of their Falcon Heavy launches, because these are big, heavy satellites being launched to geostationary orbit. but they'll put up, a follow-up, and they'll take over in multi-generational those. So those are the ones that would be very interesting to look at. There's certain classes of those, like they get kind of long in the tooth and they want to reuse frequencies and such, so that may be disqualifying them. But why would we put these things up in geostationary orbit as opposed to geosynchronous orbit, and what's the difference between the two? Well, if you think of a TV satellite, some of the satellite services, so you pay money, you subscribe to a satellite TV service, you have a broadband receiver here on the ground, and then you tune in to different frequencies, and you get different channels. Well, the satellite is sitting close to the equator and almost directly overhead North America. And you can see the footprint of the radio signal that's being sent down covers a very large area. So it needs a lot of power to do that. But if you live in the north central part of the US, you're not going to get as good a signal as, let's say, Florida, which is down south. And the reason for that is if the satellite is sitting over the equator, because it's in a geostationary orbit, like it's always in the same place at the sky, if you ever go to a city and you look at all the DirecTV satellite dishes, look at that. They're all pointing in the same direction because they're all pointing to the same satellite. If you go farther north, yep, they've also got those satellites. But if you go to the Midwest, to the northern part of the US, their satellite dishes are pointed low to the ground. They're almost at the horizon because it's got to look down to the satellite. And once you get up to northern Alaska, I'm sorry, you'd have to point below the horizon to see the satellite. So no satellite TV for you. That's called a radio footprint of a geostationary satellite. And the difference between geostationary and geosynchronous is geosynchronous can be at any tilt. It's just rotating as fast as the Earth is turning. Geostationary says it's over the equator, so it's kind of like always looking over the same spot on the Earth 24/7. And you can see those are very high up, 22,000 miles up. Now, there's two kinds of antennas you're going to find on satellites up there. There's what is known as mission antennas and command and control antennas. The mission antennas are like the big dish pointed down, big footprint covering an area or whatever. Or it could be flat panels that do phased type of things electronically. And then you'll see just little tiny antennas that are tiltable, that are focused on a specific spot. That's where the ground station is for management of the satellite. And then you'll see just, spiky looking like these little triangular ones. And those are field antennas for like GPS array kind of things. So there's different kinds of antennas. But what you'd want is something that could receive in a certain frequency and point the antenna and be a large parabolic dish so it can collect weak signals from up in space. And you want that to be geostationary, so you could point it up and it's always in the same spot. Or maybe geosynchronous, you didn't mind it orbiting, but you need to make sure you have a ground station that's always in touch with it. If your mission-specific antenna is a parabolic dish, this is really great because there are some secret satellites that are up there that have gigantic parabolic dish antennas, and they can receive over a very wide range of frequencies. So that would be really cool. And then you have ones that, like the Starlink satellites, that just have a couple of very small flat plates, and those are phased arrays, so they can't see over a wide area. They, wherever the satellite is going across the sky and pointing down, that's literally like the very narrow field, and that's all they can do is scan that area. So you want the big dish. It's an older model, but here's what they call surveillance or clandestine or spy satellite. This is a picture of one that was actually up in orbit. I think it was taken by the space shuttle because that would be the only thing that could take this kind of picture of it. And it'd have to be before it went up to geosynchronous, because once it's up at geosynchronous, ain't nothing up there that's going to take a picture of it. But you can see that this one actually has two large parabolic dish antennas. One that's kind of off to the side and one that's facing down. The one that's facing down, you can see it's not solid. It's kind of an open mesh. So that tells you that it's a lower frequency, longer wavelength, because you don't need a solid metal dish. But the upper dish, that's a shorter wavelength, higher frequency, where you need a solid dish to be able to collect the radio signal. And all those little black things, solar panels. That's how much radio power it needs. So if there was a way to repurpose one of these suckers, that would be really cool. By the way, this big dish on the bottom is 100 meters in diameter. If you know the math, that sucker is over 300 feet across. So here's I actually got a schematic diagram of that big dish so I could see more details about it. But you can either have one big dish, or you can have a bunch of little dishes as an array, and you can do a phased array, like do a very long baseline interferometry of multiple satellite receivers out in space, pointed out in space. Now, how would you get all those satellites up there? Well, I'd wait until SpaceX gets their Starship going, and they created this thing they call a PEZ dispenser, and they stack a bunch of these phased array satellite receivers, actually Starlink satellite receiver and transmitter, inside the upper stage of the rocket. And then when they want to put them in orbit, this thing just like spits out individual satellites, and they all go to their place in orbit. So you can either give me this 300-foot dish antenna, which would be great, or wait until next generation Starlink's working, and you can spit out like, maybe 100 individual satellites, but that's going to cost a lot of money. I'll repurpose that clandestine big dish a lot cheaper and sooner. You want that big dish to point away from the Earth to avoid all the radio noise we have down here. You want it to point away from the sun, the Earth, and the moon, because those things produce radio noise. It'd be nice if it was out at Lagrange point L2, along with Gaia and JWST and Euclid now, but that'd take a separate mission. So that's just, beggars can't be choosers. We'll take what we can get that's already here. You'd like to have the radio telescope have, a narrow field of view and a high resolution, so you can spot small things. And think of it for a moment. If you have a clandestine satellite and it's picking up mobile phones of individual bad people in the Middle East, it can narrow the beam down and pick up a specific band of frequencies and track it. So, I think they've got the receiver electronics on board that can do that. This will be really cool for detecting the first black dwarf stellar remnant, which is the whole reason of doing this particular presentation. Is I need something that can detect the longer wavelengths, and these kind of things can do that. And how do I get one up there without waiting for a decade or spending billions of dollars? Why don't we repurpose what we've got that we're no longer using? So where are these things parked? They're parked in what is known as graveyard orbits. So these would be geostationary orbits. So they're out at 23,000 miles, and they're along the equator, but they're not over North America. They're out over the Pacific. So these satellites, when they first go up there, have, depending upon how much was spent on them, they'll have a 15 to 25 year lifespan. That's kind of like your NOAA GOES satellite stuff. And they'll move them over to graveyard. But it turns out that there's too many of those. So they needed an even more graveyardy graveyard. So they found out that if you bump these suckers up another 300 kilometers to even a higher orbit, that puts them into a non-geosynchronous. They're now moving slower than the Earth rotates, so they'll slowly precess across the sky. But those orbits being that much farther out, nothing's going to bring them down sooner because there's so little atmosphere up there that you don't have to worry about the atmospheric friction bringing them down. These are orbits that could last for hundreds of years to thousands of years. So you talk about space junk. What about the geosynchronous satellites that there's 283 of them already up there that they've already put onto graveyard orbits, and they're running out of good graveyard orbits. So they decided to move them to super synchronous, put them out even further, because now you've got the entire circumference of the equator at that higher altitude for graveyarding satellites. So yeah, be nice to get one of those suckers, because I don't care if they're orbiting the Earth. If I can repurpose it and it's farther out, that's less radio noise from the Earth. You know, if there's a little fuel left or it goes bad, it's already in a graveyard orbit. So if we can get even 5 years use out of it without spending billions of dollars to launch it up there, that would be good. But we can't use satellites that have been what is known as passivated. That's a tombstone, by the way. It's actually a Unicode font character that I just put in a text box and then blew up the font. If they have a satellite that they want to reuse the frequencies, don't want to go back to the FCC and get new ones, but this thing would be transmitting on the same frequencies as the newer one, they do what is known as passivate them. They'll put them up to this super synchronous orbit, and then the last commands they'll give it are start dumping your remaining fuel. Now it's out into space at the highest possible orbit, so the fuel is not going to ignite, it can explode. It's just going to evaporate out into space, and it's such a small amount of fuel that remains that noise, as the saying goes, until you start doing it millions of times, and then it might be something to worry about, because the fuel is heavier than hydrogen and helium, so it's not going to eviscerate out into space. It's going to just create a new layer. So they're going to dump the remaining fuel slowly. Satellites typically spin. There's a part that you know, for the solar panels to always try and cook itself and even out the heat and face the sun, they slowly rotate the satellites. And if you're familiar with the old Telstar satellites, they used to do that to evenly heat the satellite in the presence of sunlight and to make sure that the solar panels always get even exposure. They put the solar panels on the outside, and the satellite looks like a giant cylinder, and it's slowly spinning. So to reduce the chance of a mechanical fault causing the satellite to go wobbly, they'll slow the spin rate to a stop. But when they do that, it can no longer get good photovoltaic power, and the satellite will lose its fuel and lose its power and go cold and dead, and now it's just really in a graveyard up there. So we want to repurpose a satellite for radio astronomy. It makes the presumption they have not yet passivated it. And I had to come to grips with flip-flop or flip-flip. If the satellite was designed to point down, and both its mission antenna and its command and control antenna are both kind of fixed downward, and you want to make the satellite point upward, well, the antennas are kind of on the bottom side of the satellite. You can't make them like look up through the satellite, so you got to flip the satellite upside down, and now it points out into space. But that's okay for its mission antenna. But what about its command and control antenna? The ground station's still on the ground. If you can't bend that small antenna down far enough to point to the ground, you have to do what is known as a flip-flop. It's pointing down. It receives commands by the command and control antenna that says, okay, as of this time, I want you to rotate upward, and you'll lose contact with the Earth. You do your reception on a certain frequency, pointing at a certain part of the sky for a certain period of time, and after you've done that program, you'll flip yourself back down, or the flop part, you'll flip yourself back down, and then you'll stop using your main antenna and you'll start using your command and control antenna, and you'll send down the data you've gathered in contact with the Earth. Okay, got the new program. Point to space, do your thing, record the data, point back down, transfer the data. Maybe it can do that. Maybe its gyroscopes aren't functioning. Maybe it can't do that. You want to do this on a regular basis, you've got to use the inertial management, the gyroscopes to do it. You don't want to be expending fuel every time you do that. But if you have to have if you have no satellite, or you have to do a flip-flop for, maybe a few years just to prove it out, I'm okay with a flip-flop. I think it's programmable. Here's something else to think about. If you're going to do the flip-flop, how much storage does the satellite have? Data storage. If the satellite is a relay kind of satellite, it doesn't have to store much data. It gets the message, it sends the message. It gets the message, it sends the message. In fact, on different channels, it can be receiving and sending at the same time when it's pointed down. If it has to do a flip-flop, when it's pointed up and it's observing, all the data it's receiving has to be stored within the satellite until it flips back down again. If it's a relay satellite, it may not have the storage capacity to do that, because if it's a 15-year-old satellite, it won't have terabytes worth of solid state contemporary storage. It might only have hundreds of megabytes. And if you're receiving at a very high frequency, that's a lot of data. So it may be impractical to do this based upon, if you have to do a flip-flop and you don't have much storage, that's not a candidate satellite. So next candidate. Now, you'd like it to be what is known as a frequency agile satellite. If the satellite was for a specific purpose, like a TDRS relay satellite, it only transmits on these frequencies, it receives on those frequencies, it has a certain number of dedicated channels, and it can't, I want to listen somewhere else because I'm doing radio astronomy. If it's not a frequency agile receiver, if it can't tune to different frequencies and bands, then it's less meaningful. But if all we get is one that's got a specific band, we can start there, but it may not be the best. Now, what would be a frequency agile satellite? Those clandestine satellites where, they're hovering over the bad guy's territory, and he might be on his cell phone, he might be on a VHF radio, he might be, watching a TV broadcast. So you need to list them on different frequencies, different bands. So the clandestine satellites, or the signals intelligence satellites, would be a better choice than communications relay satellite. So we pick a satellite. It seems to be the right kind of satellite. And now we have to worry about, where does it get its juice from? How does it get power? Well, you're not going to find its, radioisotope thermoelectric generator orbiting the Earth in case it falls out of the sky. That would be a bad thing. So they're all solar powered, photovoltaic cells. If the satellite's used to pointing down, and it's over a particular place of the Earth, or it's rotating around the Earth, the sun is going to be at different angles. So the solar panels have to be able to tilt based upon the satellite either going around the Earth and being able to tilt all the time, or the satellite being in a certain spot above the Earth, and based upon a 24-hour day, okay, you'll have the sun for, 11 hours a day, because you're up high. It's not 12, it's 11. You get the sun for a while. So you don't have to make the panels tilt like 180 degrees. You only got to tilt maybe 20 degrees just to get the sun. Well, if you're going to turn the satellite upside down to point into space, and the solar panels can only tilt 20 degrees, they're rarely going to be pointing at the sun anymore. So you need a satellite that is not geostationary, but geosynchronous, so it has the ability to tilt the panels over a wider range of angles, unless they just happen to pick up what is known as a standard bus design. A lot of the satellites look very similar. That's because the structure, the mechanisms, the solar panels, those are all cookie cutter, and you go, I'm building a new satellite. What do I need? Well, let me go grab the European Space Agency 5B bus, and then I'll build my purpose-specific satellite to that. Well, you'll get the main dish and the solar panels and the motors for them and your inertial navigation and your transmitter receiver electronics for your mission control. All that's a done deal. It's off the shelf. You just pay for it and get yourself some. So if one of those buses happens to be one where the solar panels are fully tiltable, that would be great. But until you do the evaluation, you're never going to know. What about the ground station? Well, if we are going to repurpose a clandestine satellite, they don't want the burden of some radio astronomers because their network is covert. The satellite that you're going to repurpose used to send data down to a top secret facility. You don't want the radio astronomy open data to be sent to a clandestine ground station. So the satellite, if you repurpose a signals intelligence satellite that's over the Pacific Ocean at super synchronous elevation, it may be controlled by the U.S. National Reconnaissance Office, the No Such Agency, the NSA, or the Central Intelligence Agency. And they have a really fine place in Australia called Pine Gap. There was actually a Netflix TV show called Pine Gap. It was very entertaining to watch. They only did it for a while and then canceled it. Not because of lack of ratings, just because they're Netflix and they can do that. I was watching it and they canceled it. So anyway, clandestine satellites in that geography on the planet are controlled out of Pine Gap. But if we're going to repurpose this for radio astronomy, I don't think the folks at Pine Gap want to man it anymore. So you may have to slide this over to, the NASA Deep Space Network. They have a dish in Canberra, also in Australia. That could pick it up. Those dishes are getting fairly booked up, at least the bigger one. Luckily, this thing is lower, or it's not out in deep space, so you don't need the big dishes at the Deep Space Network in Australia. You just need the smaller ones. So what would be a good candidate? Yes, I did pick one. I was looking for a signals intelligence satellite of the advanced Orion or Mentor generation. I wanted one that's up there that hasn't hopefully been passivated yet, one that's been around a while, one that already has replacements up there. So I found a satellite called Orion 3. Its actual identifier is 1999-024A. That's its international identifier. Its U.S. military command address is 25727. The actual launch was identified as NRO launch USA 1108. That narrowed down all the information that I needed to get. It's funny, though, if you look up the publicly available information, it's being touted as it was a South Korean communications satellite. Like, the U.S. was helping out the South Koreans, and we launched a communication satellite for their nation, and it didn't make it to geosynchronous orbit. We just, classified it as a failed satellite. But it's up there. It's going to be up there for a while. It has one of those 300-foot mesh parabolic dish antennas. It has a separate antenna for command and control. It has a very frequency agile receiver because it's signal intelligence, 23 plus years old, which means its solar panels are in decline because they're older technology. The solar wind, because it's not geosynchronous, may have pushed it down a little, may have some micrometeoroid penetration, but let's take a look at it. I know that there's already been multiple successors sent up there to replace it, so hopefully if it hasn't been passivated. Presumes that the reception technology has been declassified. It's an older radio. It's acceptable if it's a little less than geostationary, just to do proof of concept. It's okay if it lasts for a couple of years just to show that we can do it. If it gets moved to super synchronous orbit over the Pacific, that would be fine if they want to pick a different candidate. Must not have been passivated. If it has a large parabolic antenna, that'd be great. If some of its other antennas work and we can dual channel listen, that would be great too. So they'd have to transition the command and control. Hey, look, there's a picture of Pine Gap. If it's super secret, how is that possible? Well, there's commercial satellites orbiting overhead offering free public imagery and Pine Gap. Notice they have big dishes and little dishes. What would be a good place to transition it to? The Deep Space Network that NASA runs. Over in Canberra, they have one that they've got a big dish, but they've got a bunch of smaller dishes too. And one of them, it looks big, but it's only 34 meters across. This is about 100 feet. It's called DSS 36. when they did the upgrades to the Deep Space Network for the James Webb Space Telescope, they increased the receiver capacity on certain dishes, and this happens to be one of them. So it can transmit on the X and S bands for command and control, but it can receive on X, S, and Ka bands. So it's very frequency agile. So that would be cool. So how do I know it's still up there? Remember me saying that radio astronomers have to know where all the satellites are? The US government actually publishes about every month a huge catalog of all the stuff that's up there. And there are people that take that catalog and take out all the stuff that is not small pieces of junk debris that are like rocket boosters and dead satellites and live satellites. And they have a classification of live satellites that are up there. And one of them is Orion 3. And I found its what you could call orbital characteristics. And from that, you can tell a lot about it. You can tell the NORAD ID. You can tell the international ID, when it was launched and who launched it, and the fact that it's a satellite and not a rocket booster. You can tell the orbital inclination of it. So it didn't quite make it to the equator. It's 19 degrees offset from the equator. And you can tell that it orbits about 10 orbits per day. So it's not, ISS elevation. It's a little higher than ISS. So it does 10 orbits per day instead of 1 orbit every 90 minutes. You can tell a lot by some numbers. So this particular satellite is less than geostationary, but okay. But I also found out that it has no third stage booster. So even if we wanted to get this thing up higher, it's not going any higher. It has no booster fuel left. It just has orbital correction, attitude correction fuel. But at some point, it's going to start running low on that, and they might just go goose it down, give it a negative delta V, and have it retrograde and burn up. Maybe we could use it before then for a year or two. So to that end, I mentioned this last week in the presentation side notes that I sent an email off to the U.S. National Reconnaissance Office saying, hey, what's the possibility of repurposing some of your no longer classified geosynchronous orbiting satellites for radio astronomy purposes? Now, I was expecting any number of responses. One is, it just fell on deaf ears. Like, I sent it, I carbon copied myself, so I know it went out, but don't hear back from them. Fall on deaf ears. It leaves all the power in their hands. Or they could send a polite thank you, no further response, basically, go away, kid, you bother me. Or they could send a thank you, and here's the email address of an official you should talk to, or a link to our frequently asked questions page where it says, sorry, we don't repurpose, a boilerplate response. Or they could send me an email address of a program manager or a technology representative for follow-up, like, this sounds interesting. That was what I desired. After a week, what did I get? Deaf ears, no response. At this particular point, unless this video goes out, gets on YouTube, and a lot of people watch it, and somebody at the NRO or the NSA or the CIA watches it and goes, next time NASA reaches out and wants something in orbit, let's talk to them about repurposing. And, if the men in dark suits and uniforms and interesting chapeaus shows up at my front door, I'll invite them in and show them what a retired do-it-yourselfer with public internet access, an Amazon account, and a credit card can do. Why wouldn't we do the same thing with optical telescopes? If we can repurpose radio satellites for radio telescopes, why can't we repurpose, like weather satellite that take pictures every day, repurpose weather satellites for optical astronomy? And there's some reasons why we can't do that. And they come down to focal point, field of view, and critical cooling. So see the three pictures there on the right? The one at the top is the Hubble Space Telescope. The next one down is a CIA KH-11 spy satellite. They look very similar, don't they? And the one at the bottom is a GOES satellite. That's a geostationary weather satellite. If they wanted to point Hubble out to space, hey, that makes sense because it does that normally. So Hubble, if you think about it enough, is already a repurposed spy satellite. Now, how do I know that? Well, if you remember when Hubble was first sent up, all the deep space pictures came back a little blurry. That was because the mirror and the secondary were at a focal point designed for looking down. Now, this is just my opinion because it happened. This was a matter of fact. Oh, we ground the mirror to the wrong prescription. No, the mirror was ground to the right prescription. NASA got the calculations wrong and put the secondary where the camera is in the wrong place. Turns out later on, for the telescope that is going to be going up soon, the Nancy Grace Roman Space Telescope, where'd they get the mirror? The CIA had a couple of these, and they said, hey, we'll be glad to give you 2 of these mirrors to do with as you wish. And if you want to store them, it costs about $1 million a year to store them in ultra pure vacuum chambers that are cool, because otherwise the mirror will go bad on you. It'll fog up and corrode because it's silvered. And they said, you won't trick us again. And they created the Nancy Grace Roman Space Telescope, which is going up in a few years. But it's designed for a different focal length than the purpose focal length of the mirror that they're getting from the CIA and the NSA. We could take a KH-11 so long as it has a much wider range of dynamic focus, so we could point it up and have it focus to deep space. But a GOES satellite, a weather satellite, there's a problem with that. They made them cheaper. How did they make them cheaper? Well, they knew they always pointed down, so they pretty much fixed the antennas and the cameras and everything to point down. They also fixed the solar panels. So if you put bigger batteries on board, the solar panel doesn't have to tilt, because it's always going to be pointing down. And as long as you get enough battery supply to last through the shade, as the Earth rotates, then the solar panels never have to tilt. So you can make the satellite cheaper, more reliable. Yeah, but now you're going to have to do the flip-flop. And what's the field of view of a camera image when it's pointing down and it's only got to shoot as big as the curved surface of the Earth? So it's only got to shoot, let's say, the eastern half of the US. Okay, now you turn that on, you point it to space. That's going to be a very wide field of view because space is a lot farther away. So you won't get the Eagle Nebula and the Pillars of Creation. Those will just be dot pixels in the middle of a much broader image, and that's not going to do any good. The next thing is, if you're pointing down at the Earth is very bright, especially if the sun's shining on it. So your camera does not need to be cooled to like temperature of liquid nitrogen or liquid helium. But if you're pointed out into space at something really, really dark, you're going to have to be cooled to liquid nitrogen or liquid helium to get rid of the electronic noise to get a good picture. If they put these things into the next spy satellite or the next weather satellite, it's going to increase their cost, which they won't want to do. But if they did, then they could look forward to, in the future, providing NASA with repurposed weather and spy satellites under, alternative useful purpose. Just add a couple of more things to them. So in conclusion, I want to get myself a declassified signals intelligence satellite in super synchronous orbit to point it away from Earth and do radio astronomy with it. But you don't know until somebody evaluates it. So there's a lot of stuff that you have to think about the antennas and how they can point, and the solar panels and how they can point, and what you can receive on. And by the way, this picture at the bottom is of a military satellite recently launched. This is the manufacturer of the satellite getting the license to publicly present what a Falcon Heavy put up into orbit recently. Not just one enormous antenna that's, I'm going to guess, bigger than 300 feet across, but two of them. And solar panels. And I'm guessing it's the latest generation solar panels that can produce far more electricity with the same size array. I'll look forward to in another 10 years repurposing that sucker. Lots of links. Okay, so I think the potential, given that there's thousands of satellites up there and they've put in Graveyard over 200 of them, if they haven't all been passivated, there's potential to do a trial balloon just to see if they can do it. It's just, do they want to do it? Because the manufacturer of the satellites will say, oh no, you can't repurpose any of our satellites, because if they could repurpose them, that's billions of dollars they stand to lose by not having to build another one just because you want one. But if it's already up there and you can repurpose it, you can start doing new science with it now or soon, as long as the manufacturers are kept out of the decision-making loop and they just look at it from a technical evaluation perspective. I think there's a possibility of doing a prototype kind of thing. And if it turns out to be great, then maybe the next generation of satellites could include a few extras, so that instead of taking the spy satellite and just parking it somewhere, it'll have another maybe 10 years of life, useful life, after the military's already done with it. But as the saying goes, I can dream. Okay, any comments?
Well, these satellites might outlast us.
Well, the ones that are in super synchronous orbit that have been passivated, they're going to be up there for at least hundreds of years, if not thousands. So think about it this way. If we doom ourselves through some idiocy that we do to ourselves, those satellites are still going to be up there. So if in another million years, another human species comes up on this planet well after we're gone, they're going to be wondering what those shiny things are in the sky that move overhead. And once they develop optical telescopes, they're really going to wonder what the hell those things are.
And they could use them.
And I don't know that they can use them if they're passivated, but when they get the hint that they can develop things like that and they can launch them into orbit, maybe they'll be even smarter than us and they can bring one back for a museum. Wouldn't that be cool?
Yeah. Satellite. Look, the ground is passivated.
Have any of you ever heard of the Black Knight satellite?
No, I haven't. I like the red.
There is supposedly something in orbit about the Earth that was not launched by anybody that we know of, and it's been up there since the early days of NASA.
What is it? What does it do?
It's called the Black Knight. They can't get a fix on it because it's supposedly in a lower orbit, which means it should have burned up long ago, but it's still there. And it's black, nothing reflective on it. And you can't see any solar panels or large dish antennas. If it's antennas, it's all flat panel array, and it changes its orbit. And space junk doesn't do that.
Nope.
Captured asteroids don't do that. But it's been up there for a long time. So the Y-Files has a separate video on it, Black Knight. So if you're into some entertainment that leaves you with a cliffhanger at the end of, we don't know what it is, but it's definitely something there. It's a fun watch. I think it's only about 30 or 40 minutes.
What we need to do is just develop a red dwarf and go around and scoop them all up.
You know that there are companies that want to earn billions of dollars by launching booster rockets that will go up to these satellites that have run out of fuel, piggyback on their butt end, and boost them back up to their original intended altitude, because all the electronics are still working. The solar panels are still good. They just ran out of the fuel that helps keep them in their station.
Are they identified to whom they belong visually?
If we had a space shuttle that parked next to them, yes. They usually have a national flag on the outside of them somewhere. But the Black Knight doesn't. The Black Knight is just all black on the outside. It looks like a giant, if you took a piece of volcanic glass, obsidian that was very large, and you put a large piece of obsidian in orbit about the Earth at low orbit, that would be kind of like what the Black Knight is. But it changes its orbital position, so it's not a piece of captured obsidian from some volcanic eruption, because that wouldn't do that. It would always have a very predictable orbit, and if it's in low Earth orbit, the Earth's atmosphere would slowly degrade its orbit, and it would have burned up dozens of years ago. But it's still up there, and it's been up there.
So it's being operated somehow.
Yeah, so it's changing its orbit through some means of propulsion that we're not savvy to, and it's powered by some means of electrical generation that we're not savvy to. Kind of like a giant big black Tic Tac.
UFO.
Except it's not a Tic Tac. It looks like a chunk of obsidian glass. It's not as reflective. It's got a lower albedo.
They have all these delivery things they're launching, for supplies and stuff. I always thought I guess some people don't know what the Red Dwarf was an old TV series.
Yep. BBC, yeah.
Yeah, went around and collected space garbage.
Yep. Well, there are proposals by companies to create these giant cast nets that will go up there and scoop up the larger clusters of space debris, usually because some nation like China, the US, or Russia blew up some satellite and created a field of debris. And if you had a giant mesh net, you could grab that stuff and pull it back down and burn it all up.
Yeah.
For somebody who doesn't know what they're talking about, that would be something that you would cook up. For somebody that understands the norms of orbital maneuvering, that would be a nightmare. You want a Kessler effect to destroy everything in orbit? Just try and go up there and corral that stuff. You have every particle that wants to move generally in the same direction, but each piece of junk has a different mass. The moment your capture net comes into contact with it, they won't go quietly. They will bounce off your net and then start creating a random particle field inside your net. And who knows where that's going to drag your net off to with your spacecraft attached. And who knows if your spacecraft has the fuel, the propulsive force to drag the big net full of junk down on a course you want. It could go off on a tangent all by itself and strike something else. And now you've got not a particle field hitting something. You've got a giant mass plus a big heavy satellite that could hit something. There's your Kessler syndrome. So I hope there's some smarter people up there that will go, it sounds interesting, but that's dumb. Don't do dumb. Then again, I came up with my own solution, which some people might call dumb. Put a satellite in super geosynchronous orbit, and on board that satellite have about a 30-watt laser. Do not use the laser to attempt to vaporize debris. As the debris is coming over the horizon, you use the laser to push head-on the debris to reduce the delta V, as they call it, the delta velocity of the debris, to slow it down. And as you slow it down, it's going to descend. And as it descends, it will degrade its orbit and burn it up. Problem solved. Now, will it be able to do it instantaneously? No. It's going to have to be a very smart satellite that turns on the laser for specific debris fields periodically. So every time it comes up over the horizon, it'll point the beam nose to nose at it, hit it with a certain amount of energy, and then turn the beam off. because if you just want to slow it down, you want the beam to hit it head on. The moment it starts curving over, because it's at a lower altitude, curving over, you turn the beam off. Otherwise, you're going to be pushing down on top of it. And that works differently. So there's a way of doing this. But the last thing you want to do is go, I'll send up a big manly laser to geosynchronous orbit, and I'll just vaporize it. You know, when you vaporize metal and it's traveling at 20,000 miles an hour, instead of having a piece of space junk the size of a golf ball, you now have millions of micrometeoroid particles of metal that are spread over a larger area.
Well, we could create our own mini asteroid field.
Well, we've already got kind of that. We need something where a lot of people think about this, think about what could go wrong, and really think about what could go wrong, and then do something that makes sense. And I think the laser push, to me, makes the most sense. Vaporizing, no. Blowing things up, obviously not. Putting a booster on the back end of a satellite to drag it down out of orbit. Think about how much it costs to launch a satellite, how much that booster satellite to drag it back down is going to cost, and then say, you're going to do that for a piece of space junk that nobody wants to pay that for? Yeah, not going to happen. What the United Nations did was to say, all you guys launching satellites up to long duration orbits, make sure you put on additional fuel. And at the point where you've got a certain percentage of fuel left, take the remaining fuel, if your satellite is still functioning, and dive it back down and burn it up. So if your satellite is low Earth orbiting, you are now required by international law to have enough remaining fuel and call your satellite end of life when it has enough fuel left over to deliberately, purposefully burn it up over a dead zone like out in the middle of the Pacific. There are actually graveyard destinations in the northern Atlantic and in the central southern Pacific Ocean for purposefully burning stuff up to the best of your ability. And if it won't completely burn up, having it hit the ocean there. And there are huge areas of the ocean where there are no islands, that shipping traffic is not allowed to go because something could be falling out of the sky. But sometimes that stuff is more buoyant than they thought. Cylindrical chambers that you made real sturdy, and they held like liquid nitrogen or liquid helium.
Yeah.
Those things don't burn up because they're spherical. You know, they can take a little bit of atmospheric force, and they hit the ocean and they don't sink because the only opening is one small valve that's closed. So they float on the tides and they land on shore. And somebody goes, what's that on the beach? And then somebody who knows what they're talking about has to go, that's a helium tank. Don't worry about it. Or they can go, that's a hydrazine tank. Hydrazine is that very toxic to human beings, orbiting maneuverable fuel that they use to position satellites. If there's any hydrazine left in there and they vent it, it could kill people. So as soon as they see, that's a hydrazine tank, they tell the locals, cordon it off, we'll come by to pick it up. And then they send the appropriate disposal safety squad over to pick it up. If you remember when the space shuttle would land, the astronauts could not get out of the space shuttle right away. They brought that big ass propeller and parked that propeller at the rear of the space shuttle, and it literally blew wind across the space shuttle. At the rear of the space shuttle were hydrazine thrusters that once they came back down from space, they could be a bit leaky. So they could be leaking the remaining hydrazine. They tried their best to dump all the hydrazine upon reentry, but some might be left in the nozzles of the tank. So they bring the big spinny fan out there to dissipate all the possibly deadly hydrazine. And then the astronauts could come off. So if you ever wanted to know, what's the spinning propeller for at the back of the space shuttle? That's to blow away the hydrogen fumes. Once the fumes were gone, they could push the ladder up to it, and then the astronauts could come out of the balcony and go, "Hi, we're back."
You could have a whole new career opportunity as a outer space mortician.
Yes. Talk to me. I will graveyard your satellites for you. But
Yes.
then I'd have to have the command and control ground stations to talk to them. And if they're clandestine, they won't want me doing that as a commercial entity. They'll want to do it themselves. So I'll be happy if the NRO says, yeah, we're no longer going to use that one. We were about to passivate it, but we'll donate it to your company if you want to do it. But we invite you to go through the auspices of NASA. I'll be happy to go through NASA. If NASA will allocate, 1 or 2 full-time employees to do this for a period of time until it's a proven concept, that would be really great. Careful, I have a plan. Always be careful when I have a plan. Because what's the phrase? I love it when a plan comes together.
Yeah.
Okay.
Funny. Oh my goodness.
So I thought that would be a fun thing to do tonight.
It was. Very good.
As usual, more minutia than you ever thought possible.
Yeah.
But if somebody comes along and watches this video and they go, he didn't think about, yeah, okay, tell me something I didn't think about. That's what the comment section is for. So if you find something else that would absolutely positively prevent it, send a comment. Be happy to read it and review it. And if it makes sense, I'll post it and respond to it. If it's just, vile comments, those get deleted rather quickly, because the way the comments work on the Broad Astronomy YouTube and Facebook channel is they all get vetted. It doesn't just get unleashed on the public, whatever the public wants to say. It gets put in a queue. I get notification. I go look at them and go, hey, that's an interesting question. Never thought of that. And I'll respond to it. Or I did think of that. What did you do? Fall asleep during the presentation? And then they'll fess, I didn't see that. Go back and look at it again. It's at this many minutes in the presentation. Yep, you're right, I saw it. Or just vile comment and that gets deleted. So if you ever look at the comment section, you go, where's the great unwashed public? The great unwashed public gets washed off of there. But I'd be happy to answer any question anybody has. If, I learned a long time ago, there are no dumb questions. I might have a dumb answer for you, but there are no dumb questions.
There are plenty of dumb questioners.
The questioners may be unaware. They may not have it in their personal or career background to be educated in that stuff, which is usually the case, and that's fine. But just plain dumb, no, it's I have yet to find a person that's purely, as they say, dumb as a post. Because the way I look at it is, the people I'm communicating with, they were at least skilled enough and smart enough to know how to get online on a Zoom session, or they know how to post a comment to a YouTube or a Facebook page. But the one I can always rely on is they're out there driving cars with you and they're not hitting you. So they're not so ignorant that they get out on the highway and they play bumper cars all the time.
Yeah, thank God.
Yeah. We're coming up on the bewitching hour.
Yep, we are.
Oh,
One of the cats came and got me. This is time for treats and go to bed.
I wait for the cows to go home.
well, that'll be a while. It was great again. Thank you so much.
Okay. Good night, everyone.
Good night.
Good night.
Okay, good night, y'all.
Good night.